Every diagram you have ever seen of the universe tells you the same thing. The cosmos is expanding. Galaxies are flying apart. Everything is moving away from everything else, slowly, smoothly, forever. That story is true on the largest scales. But here is what it leaves out. The Milky Way is not flying apart from the universe. The Milky Way is falling. Not coasting, not drifting, falling in a particular direction at 630 kilometers per second toward a region of the sky that has never been visible from inside our own galaxy. Right now, as you sit perfectly still, you and the entire galaxy you live in are moving across the cosmos at over 2 million kilometers per hour towards something nobody can see directly, behind a wall of stars and dust we did not begin to peer through until the late 1980s. Whatever is pulling us has a name and a mass and a location. And the answer keeps getting larger every time we look. Get comfortable. Hit subscribe if you are new here, because by the end of this, the simple picture of the expanding universe will never feel quite the same again. Now, let's slowly ease into this. Part 1. The picture you already have. If you have ever seen a diagram of the expanding universe, you have probably seen the same image more than once. There are dots on a balloon, and the balloon is being slowly inflated, and as it inflates, every dot grows further from every other dot. There is no center, because the surface of the balloon has no center on it. There is no edge, because the surface curls back on itself. There is only expansion, smooth and global, carrying everything outward at the same rate in every direction at once. That picture is the bedrock cosmological story most people carry with them. It is the picture you may have learned from a textbook in school, or from a documentary late at night, or from a friend who once tried to explain general relativity to you with a piece of fabric and a tennis ball. It is the simplest possible answer to the largest possible question, which is, what is the universe doing? And the picture is, on the largest scales, correct. Cosmic expansion is real. Edwin Hubble showed in the late 1920s that the further away a galaxy is from us, the faster it is receding. The relationship is so steady and so clean that today we have a name for it. We call it Hubble's law. We have measurements of the rate of expansion that are accurate to better than 1%, depending on which method you use. We have a model of the universe, called lambda cold dark matter, that takes this expansion as one of its central ingredients. From that single observation, an entire architecture of cosmic history follows. The Big Bang, the cosmic microwave background, the slow cooling of matter and radiation, the eventual formation of galaxies and stars, and the room you are currently sitting in. All of it begins with the fact that the universe is expanding, and all of it is consistent with the picture of dots on an inflating balloon. But if you slow down and ask the picture a slightly harder question, you find that it leaves something out. The picture is true on average. It is true in the sense that if you measure many galaxies in many directions, you find that the average behavior is recession. It is true in the sense that, on scales of hundreds of millions of light years, every observer sees roughly the same thing. The universe, on its largest scales, looks the same in every direction, from every position. We call this the cosmological principle, and it has been tested repeatedly with deep surveys of galaxies and with measurements of the cosmic microwave background, and it has, so far, held up. The universe really does, on the very largest scales, look smooth and isotropic. The question that the simple picture does not answer is what happens on the scales we actually live on. Because on smaller scales, the picture changes. On smaller scales, the dots on the balloon are not perfectly distributed. There are clumps, there are filaments, there are voids. There are walls of galaxies running for hundreds of millions of light years, and there are empty spaces between them where almost nothing lives. The balloon is not uniform. The dots are arranged into a structure, and that structure has consequences. The most important consequence is the one that the simple picture quietly leaves out. The most important consequence is gravity. On the largest scales, expansion wins. The universe pulls itself apart faster than gravity can hold it together. But on smaller scales, gravity wins. Gravity holds a galaxy together. Gravity holds a galaxy cluster together. Gravity holds a supercluster together, more or less. And gravity, given enough mass concentrated in a small enough region, can pull entire galaxies through space at speeds that have nothing to do with cosmic expansion at all. The simple picture, the inflating balloon, has galaxies as passive dots riding on the surface as it grows. The real picture has galaxies that move on the surface of the balloon, drawn by the lumps of mass around them in directions that the simple picture does not predict. You probably already know that the Andromeda galaxy is moving toward us. This is one of the first counterintuitive facts that people learn about cosmology after they learn about the Big Bang. The Andromeda galaxy is roughly 2.5 million light years away, and it is approaching the Milky Way at about 110 kilometers per second. In several billion years, the two galaxies will collide and merge into a single larger one. That fact, by itself, is enough to demonstrate that the simple picture is incomplete. If everything is moving away from everything, how can Andromeda be moving toward us? The answer is that on the scale of the local group, our small family of galaxies that includes the Milky Way and Andromeda, and a few dozen smaller companions, gravity has held the family together against the pull of cosmic expansion. The local group is gravitationally bound. The expansion is happening on the largest scales around it, but inside the group, the galaxies are doing what galaxies have done since they first formed. They are pulling on one another. This is the first crack in the simple picture, and it is the crack we are going to widen tonight, slowly and carefully, until it opens onto something much larger than most people realize. Because the local group is not the end of the story. The local group itself is not at rest in the universe. The local group is also moving, and it is moving in a particular direction at a particular speed, and what it is moving toward is not a single galaxy. What the local group is moving toward is a structure no one knew existed until the late 1980s, a structure that hides behind the disk of our own galaxy, a structure whose name comes from a half-joke in a hallway conversation at a scientific meeting, and a structure that turned out, after decades of careful work, to be only the first layer of an answer that recedes faster than we can map it. Tonight, we are going to follow that question outward. We will start with a motion you cannot feel. We will go to the original discovery in 1987, when 7 astronomers in California and elsewhere first noticed that the local universe was tilted. We will travel into the zone of avoidance, that wedge of sky hidden by the dust and stars of our own galaxy, and we will see how X-ray telescopes and radio surveys slowly assembled a picture of what was hiding there. We will come to the moment when the mass did not add up, and we will follow the resolution outward to the Shapley Concentration. More than 10,000 trillion suns gathered 650 million light-years away. We will turn around and find the Dipole Repeller, an underdense region opposite the Great Attractor that pulls us forward not by pushing but by absence. We will visit Laniakea, the supercluster we live inside, and Vela, the supercluster whose existence we did not confirm until 2017. And we will arrive, at the end, at the open question, the one the next decade of observations is going to try to answer. The question is, where does the cosmic flow finally end? The question is, what is dragging the Milky Way across the universe, And how far past the maps we have does the answer reach? For now, settle in. Begin with the simple picture, the one you already know. Begin with the dots on the balloon. We are going to leave that picture behind. But it is the right place to begin, because the picture itself is half true, and the half it leaves out is what the rest of this video is about. Part 2. The first crack. The first crack in the simple expansion picture is a personal one, in the sense that it lives close to home, on the scale of the galaxies we have known about for the longest time. Long before astronomers discovered that the local group was falling, before anyone had measured peculiar velocities of distant ellipticals or mapped the cosmic web, there was already evidence that the universe was not simply pulling itself apart at every scale. The evidence was Andromeda. The evidence was, more broadly, every gravitationally bound system we could see. The evidence was the fact that galaxies, like ours, hold themselves together at all. When Edwin Hubble published his linear distance-velocity relation in 1929, the observation that defines the entire concept of cosmic expansion, his sample of galaxies covered a range of distances from about 1 million light-years out to about 6.5 million light-years. That was, by the standards of modern cosmology, a tiny corner of the universe. Hubble himself was aware that very nearby galaxies did not fit cleanly into his linear relation. The Magellanic Clouds, the small companions of the Milky Way that orbit us at distances of around 170,000 light-years, were obviously not receding. The Andromeda galaxy, at about 2.5 million light-years, was actually blue-shifted, moving toward us at about 300 kilometers per second relative to the Sunday. Hubble's law described the average behavior at large enough distances that the average behavior was the dominant signal. It did not describe what happened in the neighborhood. In the neighborhood, gravity ruled. The reason for this is simple to state and a little harder to feel. Cosmic expansion is a property of space itself. It is not a force in the conventional sense. Galaxies do not push each other apart. They do not feel a wind blowing them outward. They are carried along by the slow, steady stretching of space between them. The rate at which space stretches is described by Hubble's constant, which has a value of around 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. So, if a galaxy is 1 megaparsec away from us, the stretching of space adds about 70 kilometers per second to its recession. If it is 10 megaparsecs away, the stretching adds 700. If it is 100 megaparsecs away, the stretching adds 7,000. The further out you go, the more space there is between you and the galaxy, and the faster the recession. But gravity does not care about how much space is between two objects. Gravity cares about how much mass is concentrated in a region. And inside any region where the gravitational pull is stronger than the local expansion rate, gravity wins. The expansion stops, or rather, the expansion never really got going in the first place. The region is bound. It stays the same size, more or less, while the rest of the universe stretches around it. A galaxy is bound. A galaxy cluster is bound. A supercluster, more loosely, is bound, or partly bound, depending on how you draw its boundaries. The simple picture of the inflating balloon is true only of the surface between the bound structures. The structures themselves are like beads on the balloon, holding their shape while the spaces between them grow. This is why Andromeda is moving toward us. The local group, our family of galaxies, is gravitationally bound. The Milky Way and Andromeda are the two largest members, and they are slowly falling toward each other under their own mutual gravity. The fall has been going on for about 13 billion years, since both galaxies formed. The fall will end in about 4.5 billion years, when the two galaxies merge into a single larger structure. The combined remnant will not be a spiral like the Milky Way or Andromeda. It will be an elliptical galaxy, slowly settling into a more relaxed shape after the violence of the merger. Astronomers have given the future galaxy a name. They call it Milkomeda, or sometimes Milkdromeda, depending on who is talking. The name is a placeholder. The reality is that 4.5 billion years from now, the structure of our local universe will have changed permanently, not because of cosmic expansion, but because of cosmic gravity. The merger of the Milky Way and Andromeda is, in a sense, the easiest example to give of gravity-beating expansion. But it is not the only one. Every gravitationally bound system in the universe, from a star orbiting a black hole at the center of a galaxy to a galaxy orbiting the center of mass of its cluster, is, in some sense, an exception to the simple picture. The expansion is happening, but only between the bound systems, not within them. The cosmos is not a smooth fluid being stretched uniformly. The cosmos is a patchwork. There are regions of cohesion, there are regions of dilution, and the line between them depends on the local density of mass. Once you accept this, the next question follows naturally. If gravity beats expansion on the scale of a galaxy and on the scale of the local group, what is the largest scale on which gravity still wins? Where is the line? At what distance does the simple picture finally become true? The question has occupied cosmologists for most of a century, and the answer, as we now know, is that the line is much further out than anyone expected. Gravity does not stop winning at the edge of the local group. Gravity keeps winning, in subtle but measurable ways, out to scales of hundreds of millions of light years. The local group itself, gravitationally bound and stable, is not at rest. The local group is moving. The local group is falling, as a unit, in a direction that has nothing to do with the cosmic expansion around it. That fall is the second crack. The first crack was Andromeda, the easily visible case of gravity-beating expansion. The second crack is the motion of the local group as a whole, the bulk peculiar velocity that took decades to measure, and that pointed, when it was finally pinned down, toward a region of space no one had previously known to look at. To understand the motion of the local group, we have to back up and explain something the simple picture does not give you. We have to explain what peculiar velocity is, and how astronomers measure it, and why the measurement was so hard for so long. Peculiar velocity is the technical term for the motion of a galaxy on top of the Hubble flow. If you watch a galaxy from the Earth and measure its redshift, you get a number that tells you how fast it is moving away from you, but the number is a sum of two parts. One part is the recession due to cosmic expansion, which depends on distance. The other part is the peculiar velocity, the actual physical motion of the galaxy through space, which depends on the galaxy's interactions with gravitational structures nearby. To extract the peculiar velocity, you need to know the distance to the galaxy independently so that you can subtract off the predicted Hubble recession and see what is left. The hard part is the distance. Cosmic distances are notoriously difficult to measure. The standard candles that astronomers use, like Cepheid variable stars and Type Ia supernovae, work well for relatively nearby galaxies, but they only get you so far. To measure peculiar velocities for thousands of galaxies, out to hundreds of millions of light years, you need a different technique, one that can give you reliable distances for a large sample of objects. In the 1980s, several such techniques were developed. The most important of them, for our story, was a technique that applied specifically to elliptical galaxies, and it had a name that astronomers shortened, in the way astronomers always shorten technical things, to dn sigma. The full name is the diameter-velocity dispersion relation, and the technique exploited a relationship between the size of an elliptical galaxy's central region and the spread of stellar velocities inside it. With dn sigma, you could measure the true diameter of an elliptical galaxy independent of its distance, and then by comparing the true diameter to the apparent diameter on the sky, you could derive a distance. From the distance, you could derive a peculiar velocity. This was the tool that opened the door. In 1987, a team using this technique was about to publish a result that no one had predicted, and the result was about to change how we thought about the local universe. Part 3. The motion you cannot feel. Sit for a moment with how still you feel right now. The room around you is steady. The chair beneath you is steady. The floor is steady. The whole apparatus of your daily experience, the table where you set things down, the cup that you do not have to chase across the counter, the photograph on the wall that does not shift when you walk past it, all of it gives you a single, consistent message. You are not moving. The world is at rest. Your perception is built entirely on this premise, and, locally, your perception is right. Relative to the chair, you are not moving. Relative to the room, the chair is not moving. Relative to the building, the room is not moving. Relative to the ground, the building is not moving. The chain of reference frames stays consistent, layer by layer, as long as you stay close to home. The illusion of stillness holds, because every nearby thing you check is at rest relative to every other nearby thing. But step outside that chain, even one notch, and the stillness vanishes. The ground beneath the building is rotating. The Earth's surface, at the equator, moves at about 1,670 kilometers per hour just from the spin of the planet. That motion is invisible to you because everything around you is rotating with the surface. The air, the buildings, the trees, the entire shell of atmosphere, all of it moves together. There is no friction against a stationary background to remind you of the motion. The motion is real, but it is felt only when something else, like a Foucault pendulum or a long-range artillery shell or the path of a hurricane, gives you a reference point that does not move with you. Step into one of those frames and the stillness collapses. You are not at rest. You are spinning. You have always been spinning. The Earth itself orbits the Sunday. The orbital speed is about 29.78 kilometers per second. That is 107,000 kilometers per hour. In 1 second, the Earth moves a distance roughly equal to the length of New York City. In 1 minute, the Earth has moved through a volume of space larger than the average country. You feel none of this. The Earth's orbital motion is steady, smooth, and shared with the air and everything else around you. The Sun does not appear to move against the background of the stars, except over long stretches of time. The orbital motion is real, but invisible from inside. The Sun itself orbits the center of the Milky Way galaxy. The orbital speed is about 220 kilometers per second. That is roughly 7 times faster than the Earth around the Sunday. The orbit takes about 230 million years to complete one trip around the galactic center. Since the formation of the solar system, 4.5 billion years ago, the Sun has gone around the galaxy roughly 20 times. The dinosaurs lived through about a quarter of a single orbit. Modern humans, in our entire evolutionary history, have moved through less than 2/1000 of one circuit. The motion is enormous. The motion is, by any human standard, completely beyond intuition, and it is, again, invisible. Everything around the solar system is orbiting in the same direction at roughly the same rate. There is no wind. There is no scenery rushing past. There is only the slow, steady drift of the galactic neighborhood, which feels like nothing because everyone is moving together. Now stack on top of that. The Sun, dragging the planets with it, drifts through a particular region of the galaxy called the local interstellar cloud, at a speed of about 22 kilometers per second relative to the cloud. That motion is smaller than the orbital speed, but it is there. The Milky Way galaxy is moving toward Andromeda at about 110 kilometers per second. The local group, the family of galaxies that contains both the Milky Way and Andromeda, has its own bulk motion through the universe. And here, finally, we arrive at the velocity that this video is about, the velocity that almost nobody knows the number for. the velocity that does more, in a typical human life, to move you across the cosmos than every other velocity above combined. The local group is moving, as a unit, at about 630 kilometers per second relative to the rest frame of the cosmic microwave background. The cosmic microwave background is the faint glow of light left over from the Big Bang, the most uniform thing we have ever measured. It fills the universe in every direction, and it provides, for cosmologists, the closest thing to a universal reference frame that the universe has. The CMB rest frame is the frame in which the cosmic microwave background looks the same in every direction. If you are moving relative to that frame, the CMB looks slightly hotter in the direction you are moving and slightly cooler in the direction you are moving away from. The hot and cold pattern is called the CMB dipole, and it was measured by the COBE satellite in the 1990s, and then more precisely by WMAP in the 2000s, and most precisely by the Planck satellite, whose 2018 analysis pinned the dipole amplitude to about 3.36 millikelvin. From the dipole, you can derive the solar system's velocity relative to the CMB rest frame, and the answer is 369.82 kilometers per second, plus or minus 0.11, in a direction toward the constellation Leo. That is, the solar system's velocity. To get the local group's velocity, you subtract off the Sun's orbit around the galactic center and the Milky Way's orbit around the local group's center of mass. When you do the arithmetic, you find that the local group as a whole is moving at about 630 kilometers per second in a direction toward the constellations Centaurus and Hydra. That direction is roughly opposite to Leo. The number is, in cosmological terms, enormous. It is roughly 2,268,000 kilometers per hour. In the time it takes you to draw a single breath, the Milky Way moves about 3,000 kilometers in that direction. In an hour, 2 million. In a day, 54 million. In a year, just under 20 billion. The chair you are sitting in is moving toward a specific spot on the sky at a speed faster than any motion the human species has ever directly experienced. And the motion has no source you can point to. You cannot feel it. The chair does not slide. The cup does not spill. The photograph does not tilt. The motion is shared with everything around you, with the air, with the building, with the planet, with the sun, with the entire galaxy, with every star, in every spiral arm. There is no wind blowing past. There is no scenery rushing by. There is only the slow, steady, completely invisible drift of the local group, which has been falling towards Centaurus and Hydra for the entire history of life on Earth, and which will go on falling long after our species is gone. This is the second crack in the simple picture, and it is the one I want you to sit with for a moment. The chair you are sitting in is falling, not metaphorically, not in some abstract relativistic sense. Literally, the chair is moving, with you in it, at 630 kilometers per second, in a particular direction, toward a region of the sky that no one knew was special until 35 years ago. The motion was always real. The chair was always falling. You have, in your entire life, never had a single instant of cosmic stillness. There has been no moment, no second, no fraction of a second, in which the chair was at rest with respect to the universe. The motion was already happening when you were born. The motion will continue when you are gone. The chair is falling, and the only thing that has changed in the last 35 years is that we, the human species, have finally noticed. The first thing the noticing produced was a question. If the local group is falling, what is it falling toward? Something must be pulling it. Something must be there. And so the next chapter of the story is the search for that something. The search that began on graph paper in California in 1987, and that has, over the decades since, taken us deeper into the structure of the local universe than anyone before 1987 had imagined was possible. Part 4. the Seven Samurai. Discoveries in astronomy rarely look like discoveries while they are happening. They look like long stretches of data collection, and longer stretches of data analysis, and stretches longer still of arguments about whether the data is good enough to support the conclusions that someone has drawn from it. The story of the Great Attractor, the gravitational source we are about to spend the rest of this video describing, is one of those discoveries. It happened slowly, in the early to mid-1980s, in offices in California and Cambridge and Australia and elsewhere, and it took years before the 7 astronomers involved fully understood what they were looking at. When the understanding came, it came in the form of a paper that began very modestly and ended by describing the largest gravitational structure anyone had ever measured. The 7 astronomers were Donald Lyndon Bell, who was based at the Institute of Astronomy in Cambridge, England, Sandra Faber and David Burstein, both based in the United States, one at Lick Observatory and one at Arizona State. Roger Davies, also Cambridge, but originally Australian. Alan Dressler, who was based at the Carnegie Observatories in Pasadena. Roberto Turlevich, also Cambridge, Argentine-born, and Gary Wegner, who was at Dartmouth College. The 7 of them had been collaborating since the late 1970s on a long-term project to measure the distances and properties of elliptical galaxies using the DN sigma technique I described in the last part. The project had begun as a study of how elliptical galaxies form and evolve. It became, almost by accident, a survey of the local universe's gravitational landscape. The way the project drifted into cosmology is worth pausing on, because it tells you something about how scientific discoveries actually work. The team had been measuring distances to elliptical galaxies for years. They had a sample, by the mid-1980s, of more than 400 ellipticals scattered across the southern and northern skies. For each galaxy, they had a measured velocity, which came from the galaxy's redshift, and an independent measured distance, which came from dn sigma. The Hubble flow predicts a specific relationship between distance and velocity. If you take the measured distance and multiply it by Hubble's constant, you get the velocity the galaxy should have if cosmic expansion is the only thing moving it. If the measured velocity is larger than the prediction, the galaxy has a positive peculiar velocity, meaning it is moving away from us faster than expansion alone explains. If the measured velocity is smaller, the galaxy has a negative peculiar velocity, meaning it is being pulled toward us against the expansion. By computing the difference for each galaxy, the team had, for the first time, a large catalogue of peculiar velocities for a significant volume of the local universe. The original purpose of the catalogue was to study the distribution of elliptical galaxies and to refine the dn sigma relation itself. Cosmology was not the goal. But somewhere along the way, in 1985 or thereabouts, the team noticed something strange. The peculiar velocities did not look random, they looked organized. The galaxies in one part of the sky tended to have positive peculiar velocities, moving away from us faster than expected. The galaxies in another part of the sky, opposite the first, tended to have negative peculiar velocities, moving toward us faster than expected. The pattern was not subtle, it was systematic. And it was, in its overall shape, dipolar, meaning the sky was tilted, with one half pulling galaxies one way and the other half pulling galaxies the other. When they plotted the residual velocities on a sky map, the arrows pointed somewhere specific. They pointed toward a region in the southern sky, in the constellations Centaurus and Hydra, at a galactic latitude only a few degrees below the plane of the Milky Way. The arrows were not perfectly aligned, but they were aligned enough, on average, that no statistical analysis was needed to see the pattern. The local universe was streaming towards something in a coherent flow with a velocity of several hundred kilometers per second. The local group itself, including the Milky Way, was riding the flow. The flow was, in scale and direction, unprecedented in the history of cosmography. The team's first paper on the result was Dressler's 1987 publication in the Astrophysical Journal Letters, volume 313, page L37. The paper laid out the basic observation: a coherent peculiar velocity field of order 600 kilometers per second, pointing toward a specific region of the southern sky. The full collaboration's longer paper came out the following year, in 1988, in the Astrophysical Journal, volume 3, 26, page 19. The longer paper estimated the mass of the gravitational source. The estimate was on the order of 5 times 10 to the 16 solar masses, which is roughly 50,000 trillion suns, concentrated within a region of order 100 million light-years in radius. The source was not a single galaxy. It was not a single cluster. It was something bigger, something concentrated enough to pull entire galaxies through space at hundreds of kilometers per second, but spread out enough that no obvious counterpart existed in any existing optical survey. The team needed a name for what they had found. They called it the Great Attractor. The name was deliberately neutral, agnostic about what the thing actually was. It described only what it did. It attracted. It was great in scale. It was a placeholder until something more specific could be identified. The name has stuck for almost 40 years now, partly because it is evocative, and partly because, even today, no single object inside the structure deserves to take the title. The team itself acquired a name too. Somewhere along the way, someone, possibly Donald Lyndon Bell, possibly someone else, started calling the 7 astronomers the 7 Samurai. The reference was to the 1954 Akira Kurosawa film, in which 7 masterless ronin band together to defend a village. The joke was that 7 astronomers had banded together to study elliptical galaxies and ended up discovering something far larger than they had set out to find. The name has stuck almost as firmly as the name of the structure itself. The 7 Samurai measured the Great Attractor. The Great Attractor is what the 7 Samurai found. Now imagine yourself in one of those offices in the mid-1980s. The room has a desk, and the desk has a printer. The printer is producing pages of velocity residuals, 1 galaxy per line, each line giving a galactic coordinate and a number representing how far that galaxy's measured velocity deviates from the Hubble prediction. There is a slide rule on the desk. There is a stack of graph paper. The walls of the office are covered with sky charts. The lighting is fluorescent, slightly yellow, slightly buzzing. A mainframe in another room is processing the data, slowly, line by line. Coffee is somewhere in the room. The smell of fresh coffee is one of the few constants. Someone, Dressler probably, takes the latest output, lays it next to a sky chart, and begins to mark the peculiar velocities, color-coded by sign and magnitude, onto a transparent overlay of the sky. The work takes hours. As the overlay fills in, a pattern begins to emerge. The pattern is not random. The pattern is dipolar. The arrows in one half of the sky all push outward, away from us, and the arrows in the other half all point inward toward us. There is a clear gradient, a clear direction. The dipole points, when the work is done, into a specific patch of the sky in Centaurus, just below the plane of the Milky Way, in a region that no optical survey has ever fully catalogued, because the disk of our own galaxy stands in the way. Dressler stares at the overlay. The others come over. Someone says, half joking, that there must be a great attractor over there. The phrase sticks. The room is quiet for a long minute. Outside, the late afternoon light fades. The map is now drawn. The local universe has been tilted, and the tilt points exactly into the part of the sky we cannot see. That moment, more or less, is when the question we are following in this video began. From that point forward, the question was no longer simply, is the universe expanding? The question was, What is in Centaurus that the local group is falling toward, and why can we not see it? The answer would take decades to assemble, and as we will find out in the next part, the very first obstacle to the answer was the part of the universe that you might think you know best. The first obstacle was the Milky Way itself. Part 5. The Wall is the Galaxy. When the seven samurai pointed at Centaurus and said, in effect, that the local universe was falling towards something there, the immediate next step seemed obvious. Take a telescope, point it at the indicated patch of sky. See what is there. Count the galaxies, add up the mass, find the gravitational source. The science of cosmography, the mapping of large-scale structure, had been making rapid progress through the 1980s using exactly this approach. Redshift surveys, in which astronomers measured the spectra of thousands of galaxies and used the redshifts to derive distances, had been turning the local universe from a flat picture into a three-dimensional landscape. The Center for Astrophysics Redshift Survey, completed in 1977, had revealed for the first time that galaxies were not scattered randomly, but were arranged into filaments and walls and voids. The cosmic web was being drawn. Cosmographers were beginning to understand that the universe had a structure, but when the cosmographers tried to look at the patch of sky the seven samurai had indicated, they ran into a wall. The wall was not a metaphor. The wall was real. The wall was, in a very specific sense, the same wall that has been visible from Earth every clear night since human beings first noticed the stars. The wall was the Milky Way. The Milky Way is a flat disk. From inside, looking out, we see the disk as a band of light stretching across the sky, the part of the sky where the density of stars is highest. The band is what gave the galaxy its English name. The galactic plane, the imaginary surface in which most of the galaxy's stars and gas and dust reside, runs roughly along that band, with a tilt of about 63 degrees relative to the celestial equator. Most of the galaxy's mass is concentrated within a thin sliver above and below that plane. Looking through the plane, in any direction, means looking through far more material than looking out of the plane. That material is opaque. Optical photons, the kind of light we see with our eyes and with most ground-based telescopes, are absorbed and scattered by interstellar dust. The dust is concentrated in the same disk that the stars are in. The thicker the column of dust, the more light is absorbed. For a galaxy hidden behind a thick column of dust, the optical light that should reach us from it is reduced to a small fraction of its original intensity. For a galaxy hidden behind enough dust, the optical light is reduced to essentially nothing. Roughly 20% of the celestial sphere is hidden, in this way, by the disk of the Milky Way. The hidden region is called the zone of avoidance, a term that goes back to Edwin Hubble, who noticed in the 1920s that the distribution of galaxies on the sky had a clear deficit along the galactic plane. The deficit was not a deficit of galaxies. It was a deficit of visibility. The galaxies were there. The dust was hiding them. The Great Attractor sits inside the zone of avoidance. Its center, near the Norma cluster of galaxies, is located at galactic latitude -7 degrees, just below the plane of the Milky Way, in a direction where the optical extinction is among the highest in the sky. In the 1980s, when the Seven Samurai's papers were being published, the available optical catalogues of galaxies in this region were almost empty. The few galaxies that had been catalogued were ones that happened to fall in chance gaps between the dust clouds and the bright Milky Way stars. The overall density of catalogue galaxies behind the Great Attractor was, in optical terms, an order of magnitude lower than the density anywhere else on the sky at the same distance. The thing that was supposedly pulling the local group at 630 kilometers per second was, in optical light, invisible. This was the problem. The Seven Samurai had detected a gravitational source. The cosmographers needed to find the matter producing the gravity. The optical telescopes could not see it, so the cosmographers needed other tools. The first tool they used was the 21-centimeter radio line. Neutral hydrogen, the most common element in the universe, emits a faint radio signal at a wavelength of 21 centimeters when its electron flips between two slightly different spin states. The signal passes through dust almost unaffected. Radio surveys of the zone of avoidance, conducted through the 1990s and 2000s, began to catalogue the hidden galaxy population. The HIPAS zone of avoidance survey, conducted with the Parkes Radio Telescope in Australia and published by Patricia Henning, Lister Stavely-Smith, René Krahn-Korteweg, and others over the late 90s and early 2000s, identified hundreds of galaxies behind the disk that had never been seen optically. Each detection was a small step toward filling in the map. The second tool was near-infrared light. Infrared photons have longer wavelengths than optical photons, and they pass through dust much more easily. The 2-micron all-sky survey, known as 2MASS, observed the entire celestial sphere in the near-infrared, and its catalogue of extended sources extended well into the zone of avoidance, capturing many galaxies that were hidden in optical surveys. The 2MASS redshift survey, which followed up on the 2MASS extended sources with spectroscopy to measure redshifts, gave the first reasonably complete three-dimensional picture of the galaxy distribution in the obscured region. The picture, when assembled, showed something significant. The region behind the Great Attractor was not empty. It was full of galaxies. The galaxies had been there all along. The third tool was X-ray light. X-rays come from gas that has been heated to enormous temperatures of order 10 million degrees Kelvin, which happens naturally in the deep gravitational wells of galaxy clusters. The intracluster gas glows in X-rays, and the X-rays travel through the dust of the Milky Way without significant absorption. X-ray surveys, particularly with the ROSAT All-Sky Survey in the early 1990s, and later with Chandra and XMM Newton, mapped the hot gas in clusters throughout the sky, including in the zone of avoidance. The clusters glowed through the dust. The Great Attractor's region turned out to be unusually rich in X-ray clusters, supporting the Seven Samurais gravitational measurement. The combined picture by the late 1990s was clearer. The Great Attractor was not a single object. It was a region of unusually high galaxy density, a concentration of clusters and groups packed into a volume of order 100 million light-years across, centered roughly on a particularly rich galaxy cluster called Abell 3627. Abell 3627 is also known as the Norma cluster, after the constellation it lies in. The cluster is at a redshift of about 0.0157, which corresponds to a distance of about 220 million light-years. The cluster contains thousands of galaxies. It is comparable in richness to the Virgo cluster, which is the dominant cluster of our own local supercluster. And yet it was almost completely unknown to optical astronomy until the 1990s because it sat directly behind the Milky Way's disk. The Norma cluster has been called, in the years since its proper recognition, the embedded core of the Great Attractor. The phrase is accurate, but a little misleading. The Norma cluster is not the whole of the Great Attractor. It is the densest single object inside a much larger structure. The Great Attractor extends well beyond Norma in every direction, with additional clusters and groups contributing to the total gravitational pull. The original Seven Samurai mass estimate, 5 times 10 to the 16 solar masses, refers to the integrated mass of the entire structure, not just to Norma. So the wall, the zone of avoidance, the disk of our own galaxy, was not infinite. It was a thick veil, but the veil could be lifted with the right tools. By the end of the 1990s, 21-centimeter radio, near-infrared, and X-ray surveys had begun to reveal what was hidden behind it. The story, however, was not complete, because when the cosmographers added up all the visible matter they had now mapped, all the galaxies in 2-mass, all the X-ray gas in Rossat, all the hydrogen in Hipparchus, they ran into a new problem. The mass they had found did not seem to be enough. The Great Attractor, even with the dust lifted, did not appear to weigh as much as the Seven Samurai's gravitational measurement implied. There was a mismatch. The pull was bigger than the mass on the table. Either the Seven Samurai had overestimated the gravity, or the cosmographers had underestimated the matter, or there was something else, deeper out, that the surveys had not yet reached. That mismatch is the next part of the story, and the resolution to it, when it came, did not require new physics or exotic dark matter halos or anything weirder than ordinary cosmology. The resolution required only that the cosmographers look further, because the mass was real, the mass was there. It was just further away than anyone had initially looked. Part 6. The mass that was not there. For nearly a decade after the Seven Samurai paper, the Great Attractor sat in an awkward position in cosmology. Its existence was not in doubt. The peculiar velocity field had been confirmed by independent measurements using different techniques and different samples of galaxies. The Tully-Fisher relation, which gives distance estimates for spiral galaxies based on their rotation velocities, produced peculiar velocities that agreed with the elliptical galaxy results within reasonable error bars. The dn sigma technique, applied to a larger and improved sample of ellipticals, kept giving the same answer. The local group was falling towards Centaurus. Something was pulling it. The pull existed. What did not exist, or at least what could not be found, was enough mass to do the pulling. The zone of avoidance surveys, which from the early 1990s on had begun cataloguing the hidden galaxy population, were finding galaxies. The catalogue density was respectable. The Norma cluster, when its membership was fleshed out, contained around 600 bright member galaxies, and its total mass was estimated at around 10 to the 15 solar masses, which is roughly 1,000,000 billion suns. Other clusters in the region, like Abell 3656 and Abell 3744, contributed additional mass. The intracluster gas, glowing in X-rays, added still more. When all of the visible matter and the inferred dark matter halos were added up, the total mass within a sphere of radius about 100 million light-years centered on the Great Attractor came out to perhaps 2 times 10 to the 16 solar masses, depending on the exact boundaries and the precise mass-to-light conversions used. The Seven Samurai estimate had been 5 times 10 to the 16 solar masses. The newer surveys were finding less than half of that. The shortfall was not catastrophic, in the sense that mass estimates from gravitational measurements are notoriously sensitive to assumptions, but the shortfall was real. The Great Attractor, as visible to the cosmographers of the mid-1990s, did not weigh enough to pull the local group at 630 kilometers per second. Something else had to be contributing. The discrepancy launched a cottage industry in the cosmography community. Conferences in the 1990s featured sessions specifically devoted to the question. Working groups formed. Surveys were extended. People wrote review papers with titles like The Great Attractor, a critical review of the current evidence, and Toward a Complete Map of the Local Mass Distribution. For about 10 years, the question of where the missing mass was hiding occupied a significant fraction of the cosmography community's attention. Several possibilities were on the table. The first possibility, the most exotic, was that the Great Attractor's gravitational pull came not just from ordinary mass, but from some unknown dark mass component. Maybe the region contained an anomalously large dark matter halo that did not correspond to any visible galaxy or cluster. Maybe primordial black holes or other speculative dark matter candidates were concentrated there for reasons no one understood. These possibilities were taken seriously enough to write papers about, but they were not anyone's favored interpretation. They required new physics, or at least new astrophysical phenomena, and the principle of preferring the simplest explanation suggested that the cosmographers should exhaust the ordinary possibilities first. The second possibility was that the seven samurai had overestimated the gravitational pull. Maybe the peculiar velocities were not as large as the dn sigma analysis suggested. Maybe systematic errors in the distance measurements had biased the velocity residuals. The team itself, and other groups, returned to the data repeatedly through the early 1990s to check for such errors. Some refinements were found, but the overall picture stayed the same. The pull was real. The pull was approximately the size that had been reported. The pull was not going away. The third possibility was that the mass was real, but that it extended further out than the existing surveys had probed. Maybe the gravitational source was not just the structure within 100 million light-years that the cosmographers had been mapping. Maybe there was something beyond. Maybe the cosmographers needed to look deeper. This third possibility is the one that turned out to be right, and the breakthrough came from an unexpected direction. The breakthrough came not from looking at the Great Attractor itself, but from looking at a different region of sky, a region that had been known about for decades, but never properly understood. The breakthrough came from a reanalysis of an old discovery by Harlow Shapley, working in the 1930s, that had been waiting all this time for someone to notice that it might matter. Before we get to that, though, I want to pause on the texture of the mass mystery period. There is something a little unsettling about a gravitational measurement that does not match a matter measurement, even when the discrepancy is at the level of a factor of 2. The history of science has been written, in significant part, by discrepancies of exactly this kind. Mercury's perihelion did not match Newtonian predictions by a small amount, and the eventual resolution required general relativity. The rotation curves of galaxies did not match Newtonian predictions for the visible matter, and the eventual resolution required dark matter. Anomalies have a way of pointing to revolutions, and a factor of 2 mass discrepancy in the local universe could, in principle, have been a sign that something was wrong with our understanding of gravity itself. It was not, in the end. The discrepancy was not a sign of new physics. The discrepancy was a sign of incomplete surveys. The pull was real, the mass was real, and the gap was filled, eventually by looking further out. But during the years when the question was open, when no one knew which way the resolution would go, the field was alive with possibility. Conferences debated whether modified gravity, like MOND, could explain the bulk flow without invoking dark mass. Theorists wrote papers proposing that the Great Attractor might be a sign of pre-inflationary inhomogeneity, or of structure on scales larger than the standard cosmological model predicted, or of dark matter halos that did not host galaxies. The community took the possibilities seriously, and then, gradually, dismissed them, one by one, as better data came in. By the late 1990s, the consensus was forming that the resolution probably lay further out. The Norma cluster, and the other clusters in the Great Attractor region, were real, and they did contribute, but they were not the whole story. Something further away, perhaps 2 or 3 times further, was helping to pull the local group along. The community had a candidate for what that something might be. The candidate was a concentration of clusters at a distance of about 650 million light-years, in roughly the same direction as the Great Attractor, that had been visible in galaxy catalogues for decades, but had never been recognized as a single coherent structure. The candidate was the Shapley Concentration. Before 1980, almost no one used the name Shapley Concentration in a cosmographic context. Harlow Shapley, working at Harvard in the 1920s and 30s, had noted an unusual richness of galaxies in the constellation Centaurus, particularly in a region centered roughly on a cluster now known as Abell 3558. He published his observations in 1930 in the Harvard Observatory Bulletin, but at the time, the cosmographic significance was not clear. Shapley himself was more interested in the cluster's role in his cosmological model, which was incomplete and ultimately incorrect, and the richness of the Centaurus region did not get much follow-up attention. Decades passed. The galaxies in the region were catalogued in various surveys, but they were not analyzed as a single structure. It was only in the early 1980s, when redshift surveys began producing three-dimensional maps of galaxy clusters, that the Shapley concentration came into focus as a coherent gravitational structure. Somoji Raychaudhuri, working at Cambridge, published a paper in 1989 arguing that the cluster of clusters around a bell 3558 was unusually rich and gravitationally significant. Through the 1990s, Hernan Quintana and his colleagues, working in Chile, and Sandro Bardelli and others in Italy, conducted detailed redshift surveys of the region. The picture that emerged was striking. The Shapley concentration was the most massive structure within the local universe out to 1 billion light-years. It contained more than 8,000 galaxies organized into more than 24 rich clusters. Its total mass was greater than 10 to the 17 solar masses, which is more than 10,000 trillion suns. It spread across roughly 200 million light-years. This was the resolution. The Great Attractor was not the only thing pulling on us. The Great Attractor was itself being pulled by something larger, 650 million light-years away, in the same direction. The local group's 630 km/s motion was the combined result of two pulls. The Great Attractor accounted for some of it. Shapley accounted for the rest. The mass mystery dissolved. The matter was real. The matter had just been further away than anyone had thought to look. But the resolution opened a new question, and the new question is in some ways the strangest part of this story. Because if the Great Attractor is itself falling towards Shapley, then what does the question, what is dragging the Milky Way, even mean? The answer is recursive. The Milky Way is being dragged by the Great Attractor. The Great Attractor is being dragged by Shapley. Shapley is, presumably, being dragged by something. Where does the recursion stop? And that question, the question of how far the recursion goes, turns out not to be settled even today. Part 7. Shapley revealed. The Shapley concentration is, in some sense, the answer to the question this video is asking. If you wanted a single object to point at, a single thing that is dragging the Milky Way across the universe, you could point at Shapley and say that the thing is, in Centaurus, 650 million light-years away, and it is more massive than any other concentration of galaxies within 1 billion light-years of us. The thing is pulling on the Great Attractor, and the Great Attractor is pulling on us, and the pull adds up, and the resulting velocity is 630 kilometers per second in the direction Shapley sits. That is, more or less, the story. If we stop here, the story is mostly complete. But before we move on to the parts of the story that are not complete, I want to spend a little time on Shapley itself. Because Shapley is, by any honest accounting, one of the most impressive structures in the local universe, and almost no one outside professional cosmography knows much about it. The Great Attractor gets the dramatic name and the popular science coverage. Shapley sits behind, quieter, larger, and more important. Start with the scale. Shapley occupies a region of space roughly 200 million light-years across, at a mean distance of 650 million light-years from Earth. 200 million light-years is a length so large that it is hard to even gesture at meaningfully. The entire local group, our family of galaxies, is roughly 10 million light-years across. Shapley is 20 times larger than the local group in linear extent. If you put the local group inside Shapley, the local group would be one small dot in a much larger pattern. The number of galaxies inside Shapley is, conservatively, more than 8,000 bright members. The total number of galaxies, including faint dwarfs and satellites, is probably more than 50,000. The total mass is greater than 10 to the 17 solar masses. That is, more than 10,000 trillion suns. It is roughly 200 times the mass of the Milky Way. It is roughly 100 times the mass of the entire local group. The internal structure of Shapley is itself worth describing. The concentration is not a single cluster. It is a supercluster, which is a collection of galaxy clusters bound or loosely associated by gravity, organized into a coherent gravitational region. The dominant cluster, Abell 3558, sits near the geometric center of the concentration. Abell 3558 alone contains around 2,000 bright galaxies and has a total mass of around 1 to 2 times 10 to the 15 solar masses. Around Abell 3558, in a roughly elongated configuration, sit several other rich clusters, including Abell 3556, Abell 3562, Abell 3559, and Abell 1736. Each of these clusters has its own internal structure of galaxies, its own intracluster gas, its own dark matter halo, and they are connected by filaments of additional galaxies and groups that fill in the space between them. The total system is enormous, even by supercluster standards. Most superclusters are looser arrangements of 1 or 2 rich clusters with filaments connecting them to neighboring structures. Shapley is denser. Its clusters are more massive on average. The total integrated mass is larger than for any other supercluster within 1 billion light-years of the local group. Shapley is, by the standard cosmographic measurements, the most massive single concentration of matter in our local cosmic neighborhood. The discovery history is, as I mentioned in the last part, a slow one. Harlow Shapley, working at Harvard in the 1920s and 30s, first noted that the Centaurus region had an unusually high density of galaxies. His 1930 publication in the Harvard Observatory Bulletin described the richness, but the cosmographic significance was not clear at the time. The galaxies were known, the structure was not. Decades passed. The redshift surveys of the 1970s and 80s slowly built up the three-dimensional picture, but it took the systematic work of researchers like Somogyi, Ray Chaudhry, Hernan Quintana, Sandro Bardelli, and later Dominique Proust and his collaborators to fill in the details. The picture took shape over the course of about a decade, from the late 1980s through the late 1990s. By the time the picture was complete, the cosmographic community recognized that Shapley was the answer, or at least the second half of the answer, to the Great Attractor mass mystery. The local group was being pulled by the combined gravity of the Great Attractor and Shapley together, with Shapley contributing the majority of the total. The Great Attractor, in this revised picture, was less a destination and more a waypoint. The local group was falling, and Shapley was where the falling pointed. Now, here is the part I want you to sit with. The local group is falling toward the Great Attractor. The Great Attractor is falling toward Shapley. The structure is recursive. Each layer is pulled by a larger layer further out. The Great Attractor, considered as a self-contained gravitational system, is not at rest. It is moving as a unit in the direction of Shapley. Its peculiar velocity, measured by the same techniques the Seven Samurai used, is hundreds of kilometers per second. The Great Attractor is falling. We are falling towards something that is itself falling. Stop with that for a moment. The simple picture of cosmic expansion, the dots on the balloon, gives you a universe where galaxies recede smoothly from each other on the largest scales. The picture is true on those scales. But on the scales we actually live on the scales of hundreds of millions of light years, the universe is not flat. The universe is a stack of gravitational basins, each draining into the next. The local group is a small object in a larger basin. The larger basin is itself a small object in a still larger basin. There is no single fixed structure that you can point at and say, that and nothing else is what we are falling toward. The answer is layered. The answer keeps receding as you climb out from layer to layer. Each time you find the source of the pull, the source itself is being pulled by something further out. There is something disorienting about this. When you ask a question like, what is dragging the Milky Way across the universe, you expect an answer of a particular form. You expect a thing. You expect to be told, here is the thing. Here is the gravitational object that is doing the pulling. The Great Attractor was supposed to be that thing. Shapley was supposed to be that thing. Each of them turned out to be only a layer in a longer answer. The cosmos is not a hierarchy of single objects. The cosmos is a hierarchy of basins. Each basin holds smaller basins inside it. Each basin is held, in turn, by a larger basin outside it. There is no single object at the top of the hierarchy that is exempt from being pulled. As far as we have been able to look, every basin is being pulled by something larger. This is the recursive vertigo I want you to sit with. It is not a vertigo of cosmic loneliness, in the way that the size of the universe or the cold of deep space sometimes is. It is a vertigo of structure. The structure goes deeper than you can see. The answer is real, and it is partial, and the partiality is itself a feature of how the universe is built. The cosmos is not built like a single house with a single foundation. The cosmos is built like nested fractals. The basin you live inside drains into the basin beyond. The basin beyond drains, in turn. The recursion does not stop where you are looking. It keeps going. How far does it go? That is the genuine open question. Lambda CDM, the standard cosmological model, predicts that the recursion terminates at some scale, with bulk flows averaging to zero on the largest scales. The cosmological principle requires this. On scales of 1 billion or 2 billion light years, the model says every direction should look statistically the same, and there should be no preferred direction for galaxies to fall. But the data, as we are going to see in a later part of this video, is not yet decisive about where the termination happens. The flow we observe in our patch of the universe does not yet die at the scale that the model says it should. The recursion, as far as we have measured, may continue past Shapley. But before we get there, the story has another twist, and it is a strange one. Because while the cosmographers were finding Shapley and resolving the mass mystery, they were also, almost as a side discovery, finding something else. They were finding a region, opposite the Great Attractor on the sky, that had almost no mass at all. They were finding a void, and the void turned out to be just as important to the pull on the local group as Shapley itself. Part 8. The Void That Pulls. In the picture you have built up so far, the local group is being pulled by the Great Attractor, and the Great Attractor is being pulled by Shapley, and Shapley is being pulled by, well, that is still being worked out. The story is one of nested gravitational basins, each draining into the next, and the picture is consistent with everything you have been told in physics class about gravity being an attractive force. Mass pulls mass. Galaxies fall toward concentrations of other galaxies. The simple rule from the textbook still applies, even at these enormous scales. The picture is, as far as it goes, correct. But in 2017, a paper appeared in the journal Nature Astronomy that complicated the picture in a way no one had quite anticipated. The paper was by Yehuda Hoffman, Daniel Pomered, Brent Tully, and Hélène Courtois, and it was based on the Cosmic Flows 3 catalogue, which had compiled peculiar velocities for nearly 18,000 galaxies, out to a depth of about 500 million light-years. The team had used those peculiar velocities to reconstruct, three-dimensionally, the underlying density field of the local universe. The reconstruction worked by inverting the equations of gravity. Given the peculiar velocity at each point, you could back out, in principle, the distribution of mass that would have produced it. The output of the analysis was a three-dimensional map of where the matter in our local universe is and is not. The map confirmed, in beautiful detail, everything we had already known. The Great Attractor showed up as a concentration of mass in the right direction at the right distance. The Shapley Concentration showed up beyond it, larger and more massive. The local group sat in a relatively ordinary position within the Laniakea Supercluster, with no surprises in the immediate neighborhood. The map was, in most respects, exactly what the cosmographers had expected. But the map also showed something they had not expected. On the side of the sky, opposite the Great Attractor, in a direction toward the constellation Cetus, and at a distance of roughly 400 million light-years, the map showed a region of unusually low mass density. The region was not empty. Voids in cosmology are never actually empty, but the region contained substantially less mass than the average region of the universe at that scale. It was a deep underdensity, large enough and deep enough to be a notable feature on the reconstruction. The team named the region the Dipole Repeller. The name encodes their finding. From the perspective of the local group, the region appeared to be repelling galaxies, in the sense that the velocity field around it pointed outward, away from the underdensity, in the same way it would if there were a positive force pushing things away. The dipole, in the name, refers to the fact that the dipole repeller and the Great Attractor sit roughly on opposite sides of the sky, forming a dipole pattern in the velocity field. The local group is pulled toward one and pushed, or appears to be pushed, away from the other, but gravity does not push. This is the most important thing to understand about the dipole repeller. Gravity is purely attractive. Mass pulls mass. Less mass pulls less. There is no mechanism in standard general relativity for an underdense region to actively push anything. The dipole repeller does not push the local group. The dipole repeller is empty in a particular way, and the emptiness creates the illusion of a push. The mechanism is this. Imagine a region of space surrounded by, on average, the usual cosmic density of matter. Now scoop out some of the matter from one part of the region, leaving an underdensity. The remaining matter, all around the underdensity, still exerts the same gravitational pull it always did. But now, from the perspective of a galaxy sitting at the boundary of the underdensity, the pull is no longer symmetric. There is less mass on one side, in the direction of the underdensity, and more mass on the other side, in the direction of the rest of the universe. The net force on the galaxy is away from the underdensity and toward the surrounding mass. The galaxy is, in effect, pulled away from the void by the gravity of the mass on the far side. Now stand at the local group's position. In the direction of the Great Attractor and Shapley, there is a concentration of mass. We are pulled toward it. In the direction opposite, in the direction of Cetus, there is the dipole repeller. There is less mass in that direction than in any other comparable region of the local universe. The gravitational pull from that direction is weaker than the gravitational pull from the opposite direction, where Shapley sits. The net effect is that the local group is pulled toward Shapley, both by Shapley's positive presence and by the dipole repeller's relative absence. The two contributions add up. The amplitude of the contribution from the dipole repeller is striking. According to the Hoffman team's analysis, the dipole repeller is responsible for roughly half of the local group's 630 km per second peculiar velocity. The other half comes from the Great Attractor and Shapley together. The pull from the void, as it were, is comparable in magnitude to the pull from the most massive concentration of galaxies within 1 billion light-years of us. This is, when you sit with it, a strange fact. The single largest gravitational structure we have ever mapped in our local universe, the Shapley Concentration, with its 10,000 trillion solar masses and its 8,000 galaxies and its richest collection of clusters in the local cosmic neighborhood, is responsible for only about half of the local group's motion. The other half comes from emptiness, not from a thing, from the absence of a thing. From a region of space that contains less mass than the average region, and whose absence is therefore translated, through ordinary gravity, into a forward pull on everything around it. Imagine you are standing on a hillside. The slope falls forward into a valley where a distant city of light glows. You are being pulled forward by gravity, in the obvious way, by the slope of the ground beneath your feet. Now imagine that, behind you, where you might have expected a hill rising up to balance the valley, there is instead a slow, gentle, downhill drop, not a cliff, not a chasm, just a soft slope descending toward a quiet, empty space. The pull behind you is weaker than the pull in front of you. The asymmetry of pulls adds up in the same direction, both toward the valley. You step forward. The step is the Milky Way's 630 km per second motion. The slope in front of you is the Shapley Concentration. The soft downhill behind you is the Dipole Repeller. Both directions agree. Both directions, in the slow truth of cosmic time, point toward the same destination. The cool air rolling down from behind you, the air you can feel against the back of your neck as you stand on the slope, is the gravitational asymmetry made tangible. It is not a wind in the literal sense. There is no force pushing air or galaxies away from the void. There is only the gentle weakness of the pull from that direction compared with the strength of the pull from the other. The asymmetry has the same physical consequences as a push. A galaxy in the asymmetric region accelerates forward, away from the void, toward the larger mass concentration. The local group, in its slow fall across the cosmos, is doing exactly this. It is being pulled by Shapley. It is also being pulled, just as strongly, by the absence of Shapley's counterweight on the other side. This was, when the Hoffman paper came out in 2017, a genuinely new way to think about the local group's motion. Before 2017, the explanation had been entirely in terms of positive mass concentrations. The Great Attractor, Shapley, maybe a few additional clusters and groups. After 2017, the explanation had to include voids. The cosmic flow we experience is shaped not only by what is there, but by what is not. The map is no longer a topography of mountains. The map is a topography of mountains and valleys both, and the valleys matter as much as the mountains do. Some researchers have questioned this interpretation. The cosmic flow's 3 reconstruction is model-dependent, in the sense that turning peculiar velocities into a density field requires assumptions about how matter and gravity are related on large scales. The depth and shape of the dipole repeller in the reconstruction depend on these assumptions. Alternative interpretations have been proposed. Some researchers have suggested that the effect might be due to spatial variation in dark energy, with regions of higher dark energy density driving structures apart faster than the cosmic average. Others have proposed that modified gravity theories could account for the apparent repulsion without invoking an underdensity. None of these alternatives is favored by the bulk of the data, but they have been kept on the table as possibilities, awaiting better measurements. The mainstream interpretation, the one supported by the cosmic flows, 3 reconstruction, and by independent peculiar velocity catalogues, is that the dipole repeller is exactly what it appears to be. It is a region of below-average mass density, large enough and deep enough to produce a measurable effect on the velocity field of the local universe. Its existence is the most recent significant addition to our picture of the local cosmography, and it has changed how we think about the question this video is asking: what is dragging the Milky Way across the universe? The answer, before 2017, was the gravity of large mass concentrations towards Centaurus. The answer, after 2017, is the gravity of large mass concentrations towards Centaurus plus the relative absence of mass in the opposite direction. The Milky Way is being pulled, in equal measure, by the presence of Shapley and by the absence of its counterweight on the other side of the sky. Gravity does not push. But absence, in just the right configuration, can pull. Part 9. Our address in the cosmos. There is a particular question that does not have a clean answer in cosmology until you build up to it carefully. The question is, where do we live? Not where on Earth, not where in the solar system, not where in the galaxy. Where do we live in the universe? What is the largest gravitational structure that we are part of? What is the basin that contains us? What is the cosmic address of the chair the listener is sitting in? For most of the history of astronomy, the question did not have a meaningful answer because the relevant data did not exist. Hubble's pioneering work in the 1920s established that the spiral nebulae were galaxies far outside our own, but the larger-scale organization of those galaxies was not yet mapped. Through the 20th century, redshift surveys gradually filled in the picture. The local cluster of galaxies around the Virgo cluster was identified by Gérard de Vaucouleurs in the 1950s as the local supercluster, a flattened collection of galaxies and groups extending out to about 100 million light-years. The local supercluster, as the original name suggests, contains the local group as a small outlier on its outskirts. For decades, the local supercluster was the largest structure that astronomers reliably said we were part of. But the local supercluster has always sat in an awkward position in cosmography. Its boundaries were never very well defined. Different surveys gave somewhat different shapes and extents. The structure was clearly real, in the sense that there was a higher density of galaxies in this region than in surrounding regions. But the question of what counted as belonging to the local supercluster and what counted as a neighbor was a matter of definitional convention as much as physical structure. The cosmographers of the late 20th century knew the local supercluster was there. They were less sure about what it actually included. The problem with defining superclusters by overdensity, the cosmographers eventually realized, was that overdensity is not a clean concept on these scales. The universe has a fractal-like structure on large scales. Density rises and falls, gradually, in continuous gradients. Drawing a hard boundary between one supercluster and the next requires a threshold, and the choice of threshold is somewhat arbitrary. Some superclusters, defined by one threshold, dissolve into the cosmic web when the threshold is changed. Different surveys produce different supercluster catalogues. The local supercluster, as understood in the 1970s, was not exactly the same structure as the local supercluster as understood in the 1990s, and neither matched perfectly with the local supercluster as understood in the 2000s. In 2014, a different approach to defining superclusters was published in a paper in the journal Nature by Brent Tully, Hélène Courtois, Yehuda Hoffman, and Daniel Pomered, the same team that would later identify the Dipole Repeller. The paper used the cosmic flows, two catalogue of peculiar velocities, the predecessor to the cosmic flows, three catalogue that powered the Dipole Repeller analysis, and asked a different question. Instead of asking, where is the density highest, the paper asked, what is the watershed of the velocity field? The watershed of a region, in the geographical sense, is the area of land from which water flows toward a single common drainage basin. In cosmography, the watershed of the velocity field is the volume of space within which all the peculiar velocities point, eventually, toward a single common gravitational basin. The watershed definition has a clean physical meaning. Two galaxies are in the same supercluster if, given enough time and no cosmic expansion to disrupt them, they would both eventually fall toward the same central concentration. The boundary of the supercluster is the surface across which the velocity vectors diverge, with galaxies on one side falling one way and galaxies on the other side falling another. The boundary is, in this sense, a kind of dynamical fence. The fence is real, even if no physical structure marks its position. When the Tully team applied the watershed definition to the cosmic flows, to data, the local universe revealed a structure that the older overdensity-based definitions had not quite captured. The local group and the Virgo cluster and the Centaurus cluster and the Norma cluster and the Hydra cluster and many other groups and small clusters all turned out to share the same watershed. They were all draining, in their slow gravitational fall, toward the Great Attractor region. The volume of space within which this was true extended out to a diameter of about 520 million light-years. It contained roughly 100,000 galaxies. Its total mass was on the order of 10 to the 17 solar masses, comparable to the Shapley concentration's mass. The team named the structure Laniakea, from the Hawaiian phrase meaning immense heaven or immeasurable heaven. The Hawaiian name was a tribute to the Polynesian navigators who, using only the stars, had crossed the largest ocean on Earth, and whose tradition of astronomical mapping was a precursor to the modern cosmographic enterprise. The name was also a recognition that the structure was, in a real sense, our cosmic home. Laniakea is the supercluster within which the Milky Way lives. The Great Attractor sits near the gravitational center of Laniakea. The local group, including our galaxy and Andromeda and all their companions, sits in one of the outer arms of the structure, with the Virgo cluster nearby in our own local neighborhood. The picture, when you draw it, looks like a starfish or like a complicated coastline. Laniakea has several lobes extending outward in different directions. The local group is on the edge of one of those lobes. The Centaurus cluster, near the heart of the Great Attractor, sits at the center. Other lobes extend toward the Pavo-Indus filament, toward the Antlia wall, and toward the Fornax cluster. The boundaries are smooth but irregular. The supercluster does not have a clean geometric shape in the way a galaxy or a cluster does. Laniakea is more like a basin than like an object. For most of human history, no one had a proper name for the structure we lived in beyond the local group. We knew the galaxy. We knew the local group. We did not know the supercluster because the supercluster's boundary was not understood. Now we have a name. Now we have, in some sense, an address. The Milky Way galaxy, within the local group, within the Laniakea supercluster, within whatever larger basin Laniakea itself is part of, the address has a beginning. It does not yet have a clear end. There is, briefly, a moment of place in this picture. After all the vertigo of falling, of recursive layers of pull, of voids contributing as much as superclusters, the Tully team's 2014 paper gave us something we did not have before. They gave us a boundary. They gave us a frame within which we could say, this is where the Milky Way belongs. The watershed is real. The basin is real. The supercluster is a place, in the sense that any large-scale gravitational structure is a place. The chair the listener is sitting in is inside Laniakea, and Laniakea has a name, and the name is, in Hawaiian, immense heaven. But it is worth saying clearly what the discovery of Laniakea did not change. It did not stop the local group from falling. It did not resolve the question of where we are going. Laniakea, as a structure, is itself in motion in the larger cosmic flow. The watershed definition gives us a clean boundary for what counts as Laniakea, but Laniakea sits inside an even larger gravitational landscape, and the larger landscape is what is pulling Laniakea and everything inside it towards Shapley and beyond. The boundary is real, but the boundary is not at rest. This is the layered nature of the answer at work again. We have, at last, a name for our cosmic neighborhood. The naming did not solve the falling continues. Laniakea is our address, and Laniakea is also moving, and the destination of the motion is somewhere outside Laniakea, somewhere we have not yet mapped fully. The Tully team's paper concluded with a careful suggestion. They noted that the same watershed analysis could in principle be extended further out to identify the still larger basin that contains Laniakea and the still larger basin that contains that, and so on, until the cosmological scale of homogeneity is reached and the basins lose meaning. The full hierarchy of basins, from the local group to the cosmic horizon, is a project for cosmography over the coming decades. The first level of the project, the identification of Laniakea, is complete. The next levels are in progress. What we know, as of now, is that Laniakea is being pulled toward the Shapley concentration. The watershed of Laniakea drains, in the slow truth of cosmic gravity, toward Shapley's basin. Shapley itself defines a larger watershed, which contains Laniakea and probably a few other major superclusters at comparable distances. The mapping of that larger watershed has begun, with the Cosmic Flows 3 and Cosmic Flows 4 datasets, and it will be refined over the next decade with surveys like the Dark Energy Spectroscopic Instrument and the Square Kilometre Array. The picture, when it is finished, will give us a hierarchy of basins. The hierarchy will end somewhere where the cosmological principle takes over and the basins lose coherence. Where that is, exactly, is still being worked out. For now, the address you can give your chair is the Milky Way in the local group in the Laniakea Supercluster falling toward the Shapley concentration in a cosmic basin whose outer boundary has not yet been drawn. The address is partial. It is also, by any honest standard, more complete than any address the human species has ever had for itself before. Part 10. The supercluster nobody knew was there. If the story I have been telling you so far had a natural place to end, this part is the place where the ending should happen. The story has built up, layer by layer, the structure that pulls the local group across the cosmos. We have the Great Attractor. We have Shapley, which is the larger gravitational driver behind the Great Attractor. We have the Dipole Repeller, the void that contributes about half of the local group's motion through its absence. We have Laniakea, the watershed basin within which we live. The picture is, by any reasonable standard, complete. The cosmography is detailed. The mass mystery is resolved. The peculiar velocity vector points where it should. And then, in 2017, the same year the Dipole Repeller was identified, another paper appeared in the journal Monthly Notices of the Royal Astronomical Society. The paper was by René Krahn-Korteweg, Michel Kluver, Maciej Bilicki, Tom Jarrett, Matthew Collis, Asher Elagali, Hayden Williams, and Sam Stewart. It was published in the journal's Letters section, volume 466, page L29. The paper was titled Discovery of a Supercluster in the Extended Zone of Avoidance, using the Parkes HI Zone of Avoidance Survey. The title is as understated as scientific titles usually are. The content is not. The paper announced the discovery of a previously unmapped supercluster, comparable in mass to the Shapley concentration, at a distance of about 870 million light-years from Earth, in the constellation Vela. The supercluster had been hiding in the zone of avoidance for the entire history of astronomy. Optical surveys could not see it. The disk of the Milky Way blocked the view. Radio and near-infrared surveys, the same kinds of surveys that had eventually mapped the Great Attractor region, had now extended deeper and at a depth roughly 4 times further than the Great Attractor, and about 30% further than Shapley. They had found a third major concentration of galaxies. The Vela Supercluster was, in size and mass, in the same league as Shapley itself. Imagine this. For all of recorded human history, the Vela Supercluster has been there. It has been pulling on us. It has been part of the answer to where the Milky Way is going. The first cave painters in Lascaux did not know. The Babylonian astronomers who tracked the planets through the night sky did not know. Ptolemy did not know. Copernicus did not know. Newton did not know. Hubble did not know. The Seven Samurai, working in California in 1987, did not know. Even the cosmographers who mapped the Great Attractor through the 1990s did not know. The supercluster sat there in the same direction as Shapley, contributing to the same cosmic flow, and we did not see it until 2017, when radio and near-infrared surveys finally penetrated deeply enough through the disk of our own galaxy to detect it. This is the moment in the story when I want you to pause and notice what just happened. The story we have been building, the careful narrative of how the cosmographers figured out where we live and where we are going, contains a quiet but enormous fact. The fact is this. As recently as 2017, supercluster-scale structures larger than anything most people have ever heard of, structures comparable in mass to the largest concentration of galaxies we had previously mapped, were still being discovered behind the disk of our own galaxy. The map of the cosmos has not been finished. The map of the cosmos has not even been finished within 1 billion light-years of where we live. The Vela Supercluster's discovery in 2017 tells us that there may be more, that we have not yet looked thoroughly enough at the obscured regions, and that the answer to the question, what is dragging the Milky Way, may include structures that have not yet been named. Float, for a moment, above the plane of the Milky Way. Look down. Below you, the disk of the galaxy stretches out as a flat band of light, opaque and dense, with stars and gas and dust. From your vantage above the plane, you cannot see through it. The band hides everything beyond. Now look in the direction toward Vela. The direction is in the southern sky, in the constellation that gives the supercluster its name. From your floating position above the plane, the Vela direction is partially obscured by the disk. The light from Vela, in optical wavelengths, is reduced by the dust to a tiny fraction of its original intensity. Most of the galaxies in the supercluster are not visible. The supercluster, until the radio and near-infrared surveys mapped it, was effectively invisible from inside our own galaxy. The supercluster contains, by the Krahn-Korteweg team's estimates, somewhere between 50,000 and 100,000 galaxies. It spreads across roughly 200 million light-years in linear extent. Its total mass is greater than 10 to the 17 solar masses, which puts it in the same range as Shapley. The internal structure is filamentary, with several dense regions connected by long chains of galaxies, much like the internal structure of Shapley itself. The supercluster appears to be physically distinct from the Shapley concentration, sitting deeper along the same general direction in the sky, but at greater distance, with no obvious connecting filament. Vela's contribution to the local group's peculiar velocity is not yet fully quantified, because the peculiar velocity catalogues that go to those distances are still sparse. But the qualitative picture is clear. Vela is large enough and close enough that its gravitational pull on the local group is non-negligible. It probably contributes some additional component to our motion that was not captured by the Great Attractor and Shapley analyses of the 1990s and 2000s. The exact magnitude is being worked out as cosmic flows 4 and the upcoming cosmic flows 5 catalogues go deeper. The Kraan-Korteweg team had been looking for Vela, in a sense, for years. The team had run a survey of the southern zone of avoidance using the Parkes radio telescope in Australia, observing in the 21-centimetre neutral hydrogen line and supplementing the radio data with near-infrared imaging from the Visible and Infrared Survey Telescope for Astronomy, known as VISTA, in Chile. The combined dataset extended the catalogue of galaxies behind the southern Milky Way disk to depths and completeness that previous surveys had not reached. The presence of an overdensity in the Vela direction had been hinted at in earlier data, but the 2017 paper was the first to confirm the structure with enough redshifts to call it a supercluster. The follow-up work has been ongoing. Additional surveys, including ones using the South African Meerkat radio array, and ongoing observations with VISTA and the future Square Kilometre array, are gradually filling in the picture. The Vela Supercluster's full extent, its detailed internal structure, and its relationship to the Shapley Concentration and other nearby structures are all topics of active research. As of 2026, the supercluster's identification is secure, but many details are still being refined. Sit with the larger implication. Vela was always there. It was always pulling on us. It was always part of the answer to where the local group is going. The universe was not different before 2017 and after. The universe has been doing what it has been doing for billions of years, regardless of who was watching. What changed in 2017 was the map. The map filled in a region of the cosmic web that had been blank in our charts, became populated with a major supercluster. The motion of the local group, which had been explained in terms of the Great Attractor and Shapley alone, now had a third major contributor. This is, in a quiet way, the most important emotional realization in this whole story. Every map you have ever seen of the cosmos is incomplete. Every catalogue of large-scale structures has gaps. The gaps are not theoretical objections. They are practical limits, set by what we have been able to observe so far. The zone of avoidance is the most obvious of the limits, the swath of sky where the disk of our own galaxy blocks the view. But there are other limits too. The peculiar velocity catalogues become sparse at large distances because measuring distances to faint galaxies is hard. The redshift surveys become incomplete at large distances because galaxies become harder to see. The cosmic microwave background measurements give us a snapshot of the very early universe, but not a good measurement of present-day mass distribution. At every step, the map is constrained by the instruments we have, and the map gets better as the instruments improve. The Vela discovery is a reminder that improvement keeps happening, and that significant structures keep emerging from the gaps as the instruments get better. The discovery is also a reminder that the answer to the question, what is dragging the Milky Way, is not a fixed thing. The answer keeps growing as new structures are identified, as new contributions to the cosmic flow are added in. The version of the answer you would have heard 10 years ago was simpler than the version you are hearing now. The version you will hear 10 years from now will be richer still. The cosmos has not changed. The map of it has. For the rest of your life, the map will keep filling in. New supercluster-scale structures will be discovered, probably in the zone of avoidance, probably with surveys that combine radio, infrared, and X-ray data in ways that were not possible until recently. The motion of the local group, which was a mystery in 1987 and a partially understood phenomenon in 1998, and a more fully understood phenomenon in 2017, will continue to be a target of ongoing observation. You will not live to see the final map. Nobody will. But every decade adds a layer. The map you have now is the most complete one humanity has ever drawn. It is also, in specific known directions, incomplete in ways that will be addressed by the next generation of telescopes. And that, in turn, leads us to the question that remains genuinely open. The question is, where does the cosmic flow finally end? Lambda CDM says it should end somewhere. The data, as we are about to see, has been hinting that it may not end exactly where the model says it should. The next part of the story is about that hint and about what it might mean. Part 11. The flow that may not end. The lambda-cold dark matter model of cosmology, which is the working consensus framework for understanding the universe as a whole, makes a clear prediction about bulk flows on large scales. The prediction is that bulk flows should die away as the scale of the averaging volume gets larger. On scales of a few tens of millions of light-years, bulk flows can be sizable because individual gravitational structures dominate the local landscape. On scales of hundreds of millions of light-years, bulk flows should be smaller because the structures partially average out. On scales of a billion or more light-years, bulk flows should be very small indeed, because at those scales, the universe is supposed to be statistically homogeneous and isotropic, with no preferred direction for matter to flow toward. The specific predictions from lambda CDM with the parameters fitted to the cosmic microwave background data are that the root mean square bulk flow at a depth of about 300 million light-years should be roughly 200 kilometers per second. At a depth of about 600 million light-years, the predicted root mean square bulk flow drops to roughly 150 kilometers per second. At a depth of about a billion light-years, the prediction drops to about 100 kilometers per second. The decrease is gradual but clear. As the volume you average over gets larger, the bulk flow should get smaller in proportion to the inverse of the scale. Through the 1990s and the 2000s, peculiar velocity catalogues were not deep enough or complete enough to test these predictions decisively. The Cosmic Flows, one catalogue, published in 2011, was the first major systematic compilation of peculiar velocities for several thousand galaxies. The Cosmic Flows, 2 catalogue, published in 2013, extended the depth and the number of galaxies. The Cosmic Flows, 3 catalogue, published in 2016, reached deeper still and was the basis for the Dipole Repeller analysis we discussed earlier. Each catalogue improved on its predecessor, and each was used to measure the amplitude and direction of the local bulk flow. The results, through the 1990s and into the 2000s, were broadly consistent with the lambda CDM prediction, though the error bars were large enough that the consistency could not be tested precisely. Bulk flow amplitudes of 2 to 400 kilometers per second at depths of 3 to 600 million light-years were measured by several different groups with significant disagreements about exact values. Some groups argued the measured flows were slightly larger than the model predicted, but the discrepancies were modest and the tension was not regarded as serious. The community treated the local bulk flow as a reasonable success of the cosmological model. Then, in 2023, the Cosmic Flows, 4 catalogue was published. The team was again led by Brent Tully, with a long author list including Ehsan Kukchi, Hélène Courtois, Daniel Pomered, John Blakesley, Daniel Skolnick, Pranav Said, Yara Anand, and many others. The catalogue contained peculiar velocities for 55,777 galaxies, a roughly 5-fold increase over Cosmic Flows 3. The depth of the catalogue extended to roughly a billion light-years for the deepest objects. The peculiar velocity measurements were calibrated using multiple methods, including the Tully-Fisher relation, the fundamental plane, type Ia supernovae, and surface brightness fluctuations. When the bulk flow amplitude was measured from Cosmic Flows 4, a few months after the catalogue was released, the results were striking. A paper by Richard Watkins and collaborators, published in Monthly Notices of the Royal Astronomical Society in 2023, reported a bulk flow amplitude of roughly 400 kilometers per second at a depth corresponding to about 500 mpc per h, which is about 700 million light-years. The lambda CDM prediction at the same depth was approximately 150 kilometers per second. The measured amplitude was, by the Watkins team's analysis, larger than the predicted amplitude by more than a factor of 2. The discrepancy, in statistical terms, was at the level of about 2 to 3 sigma. That is, the probability of seeing a bulk flow at the observed amplitude purely from random lambda CDM fluctuations was estimated to be somewhere between 1 in 100 and 1 in 1,000. This is not a high-confidence detection of new physics. The convention in modern physics is that claims of fundamental discovery require 5 sigma, a probability of about 1 in 3.5 million. The bulk flow tension is well below that threshold. But the tension is also not vanishing. It is persisting across different analyses, different subsets of the cosmic flows, for data, and different methodological choices. A subsequent paper by Pranav Saeed and collaborators in 2024 did a more careful systematic analysis and confirmed the result. The bulk flow at large depths is larger than lambda CDM predicts, at a level of about 2 to 3 sigma. A separate analysis by Sasha Whitford and collaborators, using a different statistical method, found a similar result. The independent confirmations suggest that the tension is not an artifact of any single method. It is a feature of the data that survives different analyses. What does the tension mean? There are several possibilities. The first possibility is that it is, after all, a statistical fluctuation. 2 sigma tensions appear and disappear regularly in cosmology, and not every one of them turns out to be physical. The next generation of peculiar velocity catalogues, which will be produced by the Dark Energy Spectroscopic Instruments Bright Galaxy Survey, the Vera Rubin Observatory's Legacy Survey of Space and Time, and the Square Kilometre Array, will roughly double the number of galaxies with measured peculiar velocities. If the tension survives, it will tighten. If it does not, it will fade. The second possibility is that the tension is real and that it reflects a feature of the local universe within 1 billion light-years. Maybe our patch of space is slightly atypical. Maybe we sit in a region that contains an unusually large structure, or near an unusually large void, or in a more anisotropic configuration than the cosmological model has assumed. If so, the bulk flow we measure is real, but does not contradict the model on large scales. It just tells us about the specific accident of where we happen to live. The third possibility is that the tension is real, and that it reflects a feature of the cosmological model that is not quite right. Maybe lambda CDM, which works very well on most scales, is missing something on the scale of 1 billion light-years or so. Maybe there is a deviation from the cosmological principle at scales we have not previously explored. Maybe the matter distribution at large scales has more power in certain directions than the model predicts. Any of these would be a significant modification to the standard picture. There is a fourth possibility, more speculative still, and that is the possibility associated with the dark flow controversy. In 2008, Alexander Kashlinsky and his colleagues at NASA Goddard published a paper in the Astrophysical Journal Letters, volume 686, page L49. The paper used a technique called the kinematic Sunyaev-Zeldovich effect to measure the bulk motion of galaxy clusters. The kinematic Sunyaev-Zeldovich effect is a small distortion in the cosmic microwave background caused by clusters moving relative to the CMB rest frame. The size of the distortion depends on the velocity of the cluster. By measuring distortions across many clusters, you can, in principle, measure the bulk velocity of a large sample of objects. The Kashlinsky team measured a bulk velocity of 600 to 1,000 kilometers per second for galaxy clusters out to a distance of about 1 billion light-years. The direction of the flow was roughly toward the Great Attractor and Shapley, the same general direction we have been tracking throughout this video. The amplitude was much larger than lambda CDM predicted at that scale. If the result was correct, it implied that the cosmic flow continued out to scales much further than the standard model said it should. The Kashlinsky team called the phenomenon dark flow. The dark flow result was contentious from the start. The Planck collaboration, working with the more precise CMB data from the Planck satellite, published a follow-up analysis in 2014 in the journal Astronomy and Astrophysics. The Planck analysis did not detect a dark flow at the amplitude Kashlinsky had reported. The Planck team's null result has been the dominant interpretation in the community since, and dark flow as a discovery claim is not part of the standard picture. But the disagreement is not fully resolved. Different analyses of different datasets continue to give different answers. Some recent work has revived the discussion. Dark flow is, as of 2026, neither confirmed nor decisively ruled out. If dark flow is real, the implications are striking. The amplitude of the bulk motion at large scales would be much larger than the standard cosmological model predicts. The natural interpretation, the one the Kashlinsky team originally proposed cautiously, is that the flow reflects gravitational influence from structures beyond the observable universe. The structures, if they exist, would have to be pre-inflationary in origin, the relics of inhomogeneities that existed before the period of cosmic inflation and that did not get smoothed out by inflation completely. Such structures, if they sit just outside our cosmological horizon in the right direction, could, in principle, bias the local bulk flow. This is, by any standard, a speculative interpretation. Almost no cosmologists endorse it as a working hypothesis. The simpler interpretations of the bulk flow tension, the statistical fluctuation interpretation, and the local anisotropy interpretation are more conservative and more likely to be correct. But the dark flow possibility has not been killed by any decisive observation. It sits, like the bulk flow tension itself, as a live frontier of cosmography. The data, as of now, is not good enough to rule it out. Stand in your mind at the edge of the cosmic flows 4 catalogue. Below you, mapped in glowing arrows, every galaxy whose peculiar velocity has been measured. 55,777 arrows. Most of them point in roughly the same direction, toward Centaurus, toward Hydra, toward the Shapley region of the sky. The current is unmistakable. The flow is real. You can trace the arrows outward from the local group through the inner part of Laniakea, past the Centaurus cluster, past the Norma cluster, toward the Great Attractor region, past the Great Attractor toward Shapley. The arrows do not turn around. They do not weaken in the way the standard model predicts they should. They keep going. At the outer edge of the catalogue, where the measurements thin out and the error bars grow large, the arrows are still pointing in the same direction. They have not yet turned around. They are still aligned with Shapley, and probably with Vela, and probably with whatever lies beyond. Where do the arrows finally turn around? That is the question that the next decade of cosmography is going to try to answer. The dark energy spectroscopic instrument, currently observing from Kitt Peak in Arizona, will produce peculiar velocity catalogues at depths greater than cosmic flows, 4 by a significant margin, by the end of its planned observing campaign in 2026 and 2027. The Vera Rubin Observatory, which began full operations in 2025, will detect tens of thousands of new Type Ia supernovae and use them as distance indicators to extend peculiar velocity catalogues out to several billion light-years. The Square Kilometre Array, currently under construction in South Africa and Australia, will catalogue hydrogen in galaxies out to comparable depths and will provide an independent peculiar velocity dataset. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is already mapping galaxy shapes and positions across a large fraction of the sky. The Roman Space Telescope, NASA's Wide Field Infrared mission, will launch in 2027 and add further depth and area. By the early 2030s, the bulk flow question will probably be settled. We will know whether the flow really does keep going out to depths of 1 billion light-years and more. We will know whether the dark flow result is real or an artifact. We will know whether the cosmological model needs to be modified, or whether the local universe is just slightly more clumpy than the average. The answer will come from data that is being collected as you listen to this. The maps you have now are the most complete ever drawn. The maps you will have in 10 years will be better still. For now, the answer to the question, where is the cosmic flow finally headed, is this. As far as we have mapped, the flow is headed toward Shapley by way of the Great Attractor. The flow keeps going beyond Shapley, possibly toward Vela, possibly toward structures we have not yet identified. The flow may continue past the boundary of our current observational reach, into regions of space we have not yet seen clearly. Whether the flow ever truly terminates within the observable universe, or whether it persists at amplitudes that suggest influences from beyond the horizon, is a question still being answered. The arrows, as far as we have followed them, keep going. Part 12. The Chair and the Basin. We have come a long way, and I want to bring you back, slowly, to where we started. We started with a picture you already had. We started with the dots on the balloon, the universe expanding smoothly in every direction, the simple cosmological story that most people carry with them. We have spent the last hours and a half slowly complicating that picture. We have added gravity to the story. We have added the motion of the local group, the velocity that you cannot feel, but that has been carrying you across the cosmos at 630 kilometers per second for the entire span of your life. We have visited the discovery of the Great Attractor in 1987 by the Seven Samurai. We have spent time in the zone of avoidance, the part of the sky where the disk of our own galaxy blocks the view. We have followed the mass mystery, the period when the gravitational pull did not match the visible matter, and we have followed the resolution outward to the Shapley Concentration, 650 million light-years away, more than 10,000 trillion suns gathered into a single basin. We have turned around and met the Dipole Repeller, the void in Cetus that contributes to our motion not by pushing, but by absence. We have learned our cosmic address, the Laniakea Supercluster, the watershed basin within which we live. We have met the Vela Supercluster, the major structure that we did not confirm until 2017, the reminder that the map of the cosmos is still being drawn. And we have looked outward to the edge of the cosmic flows, 4 catalogue, where the arrows of the cosmic flow keep going, and where the question of how far they reach has not yet been answered. The chair you are sitting in is falling. That was the line I gave you near the beginning of this video, and now I want to give it back to you, with everything we have built up since then loaded into it. The chair is falling toward the Great Attractor, which is falling toward Shapley, while the Dipole Repeller pulls us forward from behind, while Vela contributes some additional pull from beyond Shapley, while the flow we measure keeps going past the edges of the catalogue into regions we have not yet mapped. The chair has been falling for the entire history of life on Earth. The chair will continue falling for the rest of the chair's existence. The motion is not metaphorical. The motion is real. The motion is, by the standards of any human reference frame, enormous. The motion has been there the whole time. We just did not notice it until 35 years ago. The wall also comes back. The wall is the disk of our own galaxy, the zone of avoidance, the band of dust and stars that hides about 1/5 of the sky from optical view. The wall was there at the start of this story, and it has been there at every stage. It is the wall that hid the Great Attractor until the radio and X-ray surveys of the 1990s found a way to see through. It is the wall that hid Vela until the radio and near-infrared surveys of the 2010s found a way to see through. It will, probably, hide other structures still, structures we will eventually map with the square kilometre array and with future surveys that combine multiple wavelengths to penetrate the dust. The wall has always been hiding more than we knew. The wall is the galaxy, and gravity does not push. That too comes back, in a slightly altered form. Gravity does not push, but absence can pull. The dipole repeller's contribution to our motion is by every fair measurement comparable to the contribution of the Shapley concentration. The cosmic flow is shaped not only by what is there, but by what is not. The map of the cosmos that the cosmographers are drawing, now and into the future, is a map of mountains and valleys both. The valleys matter, the absences matter. The local group is being pulled forward in equal measure by the presence of what is in front of us and by the absence of what is not behind us. When you started this video, you might have expected a single answer to the question in the title. What is dragging the Milky Way across the universe? You might have expected a name, a thing, an object you could point at. We have instead given you a layered answer. There is the Great Attractor. There is Shapley behind it. There is the Dipole Repeller across from it. There is Vela near Shapley. There is the unmapped region beyond, where the flow continues, and the answer is not yet drawn. The question has, in some sense, no single answer, because the cosmos is not built that way. The cosmos is built in basins inside basins. Each layer is partial. Each layer is being pulled by the next. This is the picture you can take with you after this video. The universe expands on the largest scales. The expansion is real, but on the scales we actually live on, the scales of hundreds of millions of light years and beyond, gravity has been organizing matter into nested basins for the entire age of the cosmos. The basins are real. The watersheds are real. The map of them, painstakingly assembled over more than 30 years of patient cosmographic work, is the most complete map of where we are and where we are going that the human species has ever drawn. The map is not finished. The map may never be finished because the structures keep being revealed as the instruments improve. But the map exists in a way it did not exist before 1987. And the map shows, more clearly than any picture before it, that the Milky Way galaxy is not at rest in any cosmic sense and never has been. You will, after this video ends, get up from the chair. You will move around your room. You will go to bed, or back to your day, or back to whatever you were doing before you started listening. The chair will stay where it is, in your house, on the floor, on the planet, in the solar system, in the Milky Way, in the local group, in the Laniakea Supercluster, falling toward Shapley, while the dipole repeller pulls it forward, while Vela adds its small contribution, while the cosmic flow continues past the limits of the maps we currently have. The chair will continue falling at 630 kilometers per second in the direction of Centaurus and Hydra, regardless of what you do. The motion is independent of you. The motion is independent of all of us. The motion was happening before any human existed. The motion will continue after all of us are gone. The only thing that is new in the long history of the cosmos is that we have, in the last 40 years, finally noticed. The basin we live in has a name now. The basin is Laniakea. The basin we are falling toward has a name too. The basin is Shapley. The next basin out, the one that contains all of this and points toward whatever is further still, does not yet have a name. The next basin out is, as of 2026, an open question. The instruments to answer it are being built. The catalogues to fill it in are being compiled. The cosmography of the coming decade will tell us where the recursion of basins finally ends, if it ends at all within the observable universe. For now, what we have is what we have. We have the local group, we have its motion, we have the Great Attractor, and Shapley, and the Dipole Repeller, and Laniakea, and Vela, and the open frontier beyond. We have a map. The map is not complete. The map is more complete than any map our species has ever had before. The map shows, in its incompleteness, exactly where the next discoveries will probably come from. The map points outward, past Shapley, into the dark of the not yet measured, where the cosmic flow keeps going, and where the question we have been asking tonight remains, in the deepest sense, unanswered. So the chair is falling. The map is partial. The wall is the galaxy. Gravity does not push, but absence can pull. The cosmos is built in basins inside basins, and we are inside one of them, falling toward another one, which is itself falling toward something we have not yet seen. This is the universe we live in. This is the universe that has always been here. The expansion is real. The falling is real. Both stories are true at the same time, on different scales, and the chair you are sitting in is part of both. You may now drift, if you have not already. You may stay, if you want to think about it a little longer. There is no rush. The motion will continue regardless. The cosmos will keep doing what it has been doing for the last 13.8 billion years, with or without our attention. But it is, in its own quiet way, a good thing to know about. The Milky Way is being dragged across the universe by structures most people have never heard of, in directions most people have never thought about, at speeds most people have never tried to imagine. Now, having spent this time with the question, you have heard about them, you have thought about them, you have, at least for the duration of this video, been awake to what was always happening. The chair is falling. It has always been falling. It will keep falling. And somewhere, in a direction this video has pointed you toward, there is a basin still waiting to be named, and a flow still waiting to be mapped, and an answer still waiting to be drawn.